Okay, so we have looked at how to find a different way of representing a system using Laplace transforms and transfer functions. In this part, we're going to look at how to find the system responses without having to solve differential equations, i.e. we're going to use transfer functions to do that. Then we're going to discuss particular systems like first order, second order systems, their key properties, and the idea of zeros and poles of a system and their relationship to stability. Okay. To find the solutions of a system, now I have a system here where input is ut, output is yt. That is represented by, the system is represented by a second order system. So it's y double dot plus 6y dot plus 8y equals to 2u. Now my input in this case is just a step signal, or unit step signal, because it has an amplitude of 1. Okay, I want to find out what a system responses is, and i.e. I want to know yt from this, and from the input of 1. Okay, so if u equals to 1, what is y? Because we have a first and second order derivatives here, they are not going to respond in a sort of very proportional way. Okay, but I don't want to solve a second differential equation, second order differential equation, and I don't remember how to do it, but I know a way of doing it. Okay, so to do that, I showed you this slide before. What I want is actually to first of all get the Laplace transform or the transfer function of the same system. Okay, it's the process we did last time, and then I'm going to solve that using the transfer functions. Okay, and there are several steps we need to go through for this. First of all, we find the transfer function of the system, and then we examine what input is. What's the input in time domain? Ut. And I'm going to apply Laplace transform to the input signal to give me the us. That's the first step. Okay, second step is to multiply the transfer function by what we obtained in step 1, which is the Laplace transform of the input. So second step, ys equals to gs times us. But that will only give me the ys, or the Laplace transform of the output response. But I want to see yt, I don't want to just ys. So to find that, we need to apply an inverse Laplace transform. Now, inverse Laplace transform sometimes requires a little bit of reformatting of your equation. And typically, we need to apply partial fraction expansion to break up the transfer function, because sometimes they have a quite complex format. We will use an example to show that. And then we can apply inverse Laplace transform. So 4 steps from the transfer function. First, find the Laplace transform of the input, multiply that to the transfer function to give me the Laplace transform of the output. And then if I need to do a partial fraction expansion, and then apply inverse Laplace transform to ys to give me yt. So 4 individual steps. Okay. Now for a system, I had it before. I've done this. This is the differential equation. I can easily find the Laplace transform of that, and the process of which we have done last time. Okay, so I've got this. Okay, I'll skip that step because we've done it before. So the transfer function of that particular system is 2 over s squared plus 6s plus 8. My input is the unit step signal is 1. So remember in my previous slide, step number 1, to find the Laplace transform of 1. Ut is 1, therefore Laplace transform is 1 over s. Okay. Now, if I just go back a little bit there, the transfer function of the system is 2 over s squared plus 6s plus 8. Now, if you're kind of half decent with your maths, you will notice that I can actually change that format slightly. Okay, I can change that to s plus 2 times s plus 4. That is the same as s squared plus 6s plus s. Now, the reason I'm doing it this way is it makes my life easier in step number 3. Okay, where I have to do partial fractions, because I know the inverse Laplace transform of s plus 2, and I also know not inverse Laplace transform of s4, but I don't know inverse Laplace transform of that. So I need to actually reformat that transfer function. Okay, so that's just a little bit of mess, or the pre-processing, if you like, before you get on with your steps. Now, step number 1, ut equals to 1. Therefore, I look at that table. 1 in time domain give me a Laplace transform of 1 over s. Okay, so I have 1 over s here, and so I get that equation number 4. That's the Laplace transform of input, step number 1. Step number 2 is probably the easiest of all 4 steps. I'll just multiply, I take a GS, multiply that by US. GS is 2 over s plus 2 plus s plus 4 times 1 over s. That's my step number 3. Step number 2. Step number 3. Now, if you look at the equation number 5, these in the denominator, I have 3 terms multiplied by together. You can't, because linear systems, we can actually add one to another. We can multiply a constant to transfer function, but we can't multiply 2 transfer functions together and assume their inverse will also be a multiplication. They are not. Okay, so I need to break them down into forms that I am familiar with, or you are familiar with. So in the denominator, I have 3 terms. There's s plus 2, there's s plus 4. They are multiplied together. I need to break them into plus additions. Okay, so that becomes something over s, something over s plus 2, something over s plus 4. That is a typical process of partial fraction expansion. The task is actually to find these values. What is A, what is B, what is C? Okay, I will do that because that's kind of sort of, school math stuff, partial fractions. I'll do that a little bit of revision later on. But for the time being, we'll just proceed and go through all 4 steps first. Okay, I found with my knowledge of a little bit of partial fractions, I found A to be 1 over 4, B is minus 1 over 2, C is 1 over 4. Okay, that will give me equation number 7. And then I'm going to change the format slightly. I'm going to move 1 over 4 to the front. So this becomes 1 over 4 times 1 over s. I'm going to move minus 1 over 2 to the front of second term as well. That becomes a minus 1 over 2 times 1 over s plus 2. I'm going to move 1 over 4 to the front of the third term. That becomes 1 over 4 times 1 over s plus 4. Okay, and that gives me equation number 8. I'm copy that to the next slide. That's my number 3. Now, step number 4 is to apply inverse. Now I'm done the partial fractions. Okay, I break them into small fractions. Therefore, I'm ready to apply inverse Laplace transform because I have 3 terms, either add or subtract. So if you look at equation number 4, inverse Laplace transform of 1 over s, think, input, when input was 1, the Laplace transform was 1 over s. If the Laplace transform is 1 over s, then the time domain is 1. So 1 over s corresponds in time domain 1. 1 over s plus 2, if you think about exponential functions, 1 over s plus some constant a corresponds to a time domain e to the power of minus a. So a here equals 2. Okay, I'm doing inverse. I'm doing from right to left. So 1 over s becomes 1. That's 1 over 4. Minus 1 over 2, that's a constant. So I'm copy that constant down. 1 over s plus 2, that's this format. A equals to 2. So I replace this by e to the minus 2t. 1 over s plus 4, again, it's an exponential function. In this time, it's 1 over s plus a, where a is 4. So the corresponding time domain signal is e to the minus 4t. And I'm going to copy 1 over 4 down. So the whole thing becomes 1 over 4 minus 1 over 2 times e to the power of minus 2t plus 1 over 4 e to the minus 4t. So 4 individual steps, if I may, just to recap. Step number 1, find inverse Laplace transform of the input. Okay, input in this case is 1, so Laplace transform is 1 over s. It may not be, okay, but we have a lookup table to help us with. Step number 2, you multiply g, that's transfer function, by us. Step number 3, you do partial fractions, break them into simple fractions or a summation of several terms. Step number 4, apply inverse Laplace transform. Okay, 4 individual steps. Now I'm going to give you a little bit of revision on how to do partial fraction. Well, I don't know why it's partial fracture, but it's partial fraction expansion method. Okay. Approach number 1, we're going to use common denominator method. Okay, my aim in my example is to break that down into something over s, or a over s, plus something over s plus 2, plus something over s plus 4. Okay, 3 terms in the denominator. Okay, so I need to find the 3 values there. Now to find that 3 values, this particular method is to say, right, if I go back from equation 2 to equation 1, I will need to find the common denominators of the 3 terms in equation 2. The common denominator is the one that's in equation 1. So it's s plus 2, s plus 4. Okay, that's our common denominator. So for the first term in equation 2, I need to make up s plus 2, s plus 4. So I'm going to multiply in red s plus 2, s plus 4 to the numerator and the denominator. Now remember, when you multiply something to a fraction, and you don't want to change anything, you multiply the same thing to the numerator and denominator at the same time. So that will make the first term comply with the common denominator. So at the bottom, I have s plus 2, s plus 4. For the second term, I have s plus 2 in equation 2. To make that into a common denominator, I need to multiply that by s and s plus 4. But I can't multiply that just to the denominator. I need to multiply the same terms to the numerator as well. So multiply s and s plus 2, 4 to the denominator, and you multiply the same terms to the numerator. Same goes for the third term. In the third term in equation 2, I have s plus 4. So I need to make up for the common denominator. So I need to multiply s and s plus 2 to the denominator and the numerator at the same time. Now I have the same denominator for all three terms. Now, as you well know, because we have three common terms, we can actually add the numerators together. So expand all that numerators, that will give me s squared a plus 6sa plus 8a. That's first term, or the numerator of the first term. Expand that, I get s squared b plus 4sb for the second term. For the third term, expand that numerator, I have c s squared plus 2c s. Okay, that's my equation number 4. So I'm going to go over to the next slide. If you look at, not yet, just let's go back to this slide. If you look at the numerator terms in here, okay, and compare equation number 4 to number 1. In equation number 1, I have only, in the numerator, only a constant of 2. I don't have s, I don't have s squared. So any coefficient of s will be 0. Any coefficient of s squared will be 0. But if I examine equation number 4, how many terms we have without s or s squared? There's only one term. So it's 8a, that's only one term without s. That s8a equals 2. How many terms we have with just s in there? We have 6as, this term here. We have 4sb, we have 2sc. But the coefficient of s in equation 1 is 0. So this term, add this term, add this term. Okay, 6sa plus 4sb plus 2sc without s should equal to 0. And also in question 1, I don't have a term of s squared. So all the coefficient of s squared, a plus b plus c, should also equal to 0. Okay, that will give me 3 conditions. I'll compare the constant, I'll compare the coefficient of s, I'll compare the coefficient of s squared. 3 comparisons will give me these 3 simultaneous, or this set of simultaneous equations. A plus b plus c, these are the coefficient of s squared. They should be 0 because I have no s squared in my original transfer function. Second one is 6a plus 4b plus 2c equals to 0. That's because I don't have any term in the original transfer function's numerator with a s. The last term is a equals to 2. This is the only term that exists in equation number 1. That's my original transfer function. Solving that simultaneous equation, I get 3 values. A equals to a equals to 1 over 4, b equals to 1 over 2. Well, it should be a minus here. And c equals to 1 over 4. So b should be minus 1 over 2. That will give me what s equals 1 over 4 over s minus 1 over 2 over s plus 2, and 1 over 4 over s plus 4. That's the same equation as I did with my example. So that's one method. Just break that down into, well, into several parts. Then you find the common denominator and compare the numerator terms or the coefficient of numerator terms. That's the first approach. And it's a bit enabling. It requires a bit of labor to get the solutions. My second method is slightly easier. It looks a bit complex in there, but it is actually slightly easier. Now, think about this. This is my original fraction. I need to break that down into a over s plus b over s plus 2 plus c over s plus 4, but I need to find the value of a, b, and c. Okay? Cover up means if you want to find out the value of a, first thing you look is what's in the denominator of that term. Okay? And what value of s will make the denominator term to 0? In this case, if I set s to 0, 1 over s will become 1 over 0. So s equal to 0 will make that denominator term to 0. Okay, so find what's in the denominator, find the s value that will make that term to 0. Then you go back to the original fraction, you cover that s up. It's the same term as you have beneath in the denominator here. Cover that up, okay? Just assume that term didn't exist. And then replace all the other s's by whatever s value make that term to 0. Okay, in this case, s equals to 0. So replace, cover s up, this s equal to 0, this s equal to 0. This becomes 2 over 4, 2 times 4. Okay, so 0 plus 2, 0 plus 4, that becomes 1 over 4. That will give you the a value, okay, or the value of a. To find the value of b, again, you look into the denominator. We have s plus 2 here. What value of s will make s plus 2 equal to 0? Minus 2. Because minus 2 plus 2 will be 0. So you go back to the original fraction, cover s plus 2 up, that's the b value. Cover that term up, set all the other s's to minus 2. So s here becomes minus 2, s here becomes minus 2. And so therefore I have 2 divided by minus 2 times minus 2 plus 4. That will give me minus 1 over 2. By the same argument, or by the same approach, if I want to find the value of c, I need to examine what's in the denominator, s plus 4, and what s value will make that term to 0. That's minus 4. So I'm going to go back there, I'm going to cover s plus 4 up, I'm going to set all the s values to minus 4. So that becomes minus 4, that becomes minus 4. That'll give me 1 over 4. That's the second method. It's called a cover up. It's actually easier to do. You don't have to solve, you don't have to find the common denominators, you don't have to solve simultaneous equations. Okay, just need to cover that thing up or cross it out, whatever you like. Okay. Now it's your turn. I have set some practice questions for you guys and find out response of the following systems. I'll give you 3 different transfer functions, but I want to know yt when they input the unit step. Second part of the practice is if I change the input to an input signal, what would you have for systems like that? Okay, in G4 and G5. Okay, so have a go, and then we can actually look at that your solutions. If you have questions, you may ask in our tutorial sessions. Okay, thank you.